Hello, good morning. Myself Dr. Shaila Dinkar Apte. Now we start with the next chapter, that is Fourier transform representation of aperiodic signals. So if the continuous time signal is periodic, we write the Fourier series representation. But if the signal is aperiodic, then we write the Fourier transform representation. So in this particular lecture, we'll understand Fourier transform of a periodic continuous time signals and Fourier transform of some special signals, right? Now, what is a transform? What we are doing by using a transform, and who has generated these transforms? The mathematicians have invented these transforms. Why they have generated these abstract things? They have generated these abstract things so that a user can analyze different frequency contents of the signal. That means you are changing the view of the signal remains the same, but instead of viewing it in time domain, we view it in the frequency domain. What happens is sometimes some special features, they become evident or they become visible in the transform domain, which were not otherwise visible in the time domain. So that is one advantage of using a transform. Second advantage of using a transform is, if we consider the time domain signal, there are many samples required to be processed, or many samples required to be transmitted from transmitter end to receiver end. But if we use a transform for the signal, most of the coefficients, let us say minimum 50% of the coefficients are zero, so those can be avoided and we can transmit only first 50 coefficients and recover it at the receiver end, and we will get the original signal. So compression is possible in transform domain. So the signal can be compressed and sent, and this will save the bandwidth of our channel. So there are several reasons of why we are using the transforms. So here we go for Fourier transform of continuous time signals. One more obvious advantage of transforms is, for a particular system, LTI system, when we write its transfer function in any transform domain, we can understand where the pole locations are. So considering the decomposition of the denominator polynomial, when we find out where the poles are, we can understand whether the system will be stable or not using just pen and pencil. That is, before the system is actually implemented, we can find out whether the system will be stable or not, and whether the system, what will be the system response for different standard inputs that can also be calculated. So this is a Fourier transform that we are discussing. The formula for Fourier transform is x of j omega is integration minus infinity to infinity x of t e raised to minus j omega t dt. And how to recover x of t? X of t can be recovered from x of omega, and we can write it as 1 upon 2 pi integration minus infinity to infinity x of j omega e raised to j omega d omega. Right, so this is the formula for inverse Fourier transform, and this is the formula for Fourier transform. We can write it also in terms of the frequency, or we can write it in terms of j omega. Now there are certain conditions to be satisfied so that the Fourier transform will exist. In order that the Fourier transform exists, the signal must be absolutely integrable. So when we write integration minus infinity to infinity, if the integration value goes to infinity, we cannot use this Fourier transform. The signal xt must have finite number of maxima, minima, and finite number of discontinuities. If there are infinite number of discontinuities, we cannot represent the signal in terms of Fourier transform. The size of the discontinuities must be finite. The discontinuity must not be such that the signal is totally divided into two different signals. It should not happen. There should be a small discontinuity, I can say. These conditions are named as Dirichlet conditions, and these must be satisfied in order that the Fourier transform exists. See, this is a sample signal that is shown with finite number of maxima, minima, and finite number of discontinuities. So such type of discontinuities are allowed, and if there are some finite number of maxima and minima, that is also allowed. And in this case we are considering a periodic signal. Remember, if it is periodic signal, in case of periodic signal there are lot many maxima and minima. So we cannot use Fourier transform representation for a continuous time signal. In that case we will have to make use of Dirac delta function, that we will see later on. But in case when the signal is aperiodic and if there are finite number of maxima and minima and finite number of discontinuities, then only we can find out the Fourier transform representation for the aperiodic signal. Now let us consider the signal which is exponential signal e raised to minus 3t ut. So it is existing only on right hand side, and it is starting with value 1 at t equal to 0, and it is exponentially decreasing. So how to find out the Fourier transform? Fourier transform x of j omega is integration minus infinity to infinity e raised to minus 3t ut e raised to minus j omega t dt. Now this ut is existing from 0 to infinity, so now the limits are changed from 0 to infinity, e raised to minus 3. Now we combine these e raised to terms, so e raised to minus 3 plus j omega t dt. Now when I take x of j omega, it is equal to, when I integrate this, I will have 1 upon minus of 1 upon 3 plus j omega e raised to minus 3 plus j omega t, and the limits will be from 0 to infinity. When it is 0, when t is equal to 0, the corresponding e raised to term will be equal to 1, and at infinity it will be equal to 0. So 0 minus minus 1, so it will be equal to 1. So this minus sign will go and we'll have 1 upon 3 plus j omega. Now let us see how the magnitude response can be calculated and how the phase response can be calculated. So let us consider the magnitude response. So consider mod of x of j omega, it is equal to 1 upon 3 plus j omega. Now what we do, we rationalize. We multiply it by 3 minus j omega and divide it by 3 minus j omega. So we'll have 3 minus j omega upon 9 plus omega square. So if we just calculate this, if we just try to find out the corresponding magnitude, it can also be written as 1 upon under root of 9 plus omega square. So if you just expand this and simplify, what I have done is I have taken this 3 upon 9 plus j omega as first term, then j omega upon 9 plus omega square as second term. I take the magnitude, square it, and then take the under root. So this is actually the magnitude of x of j omega. Now how to calculate the magnitude response? For that I'll have to go on putting different values of omega. So initially I put omega equal to 0. So what will be x of j omega? Magnitude, when omega is equal to 0, this will be just under root of 9. So 1 upon 3 is 0.3333. This is the amplitude at omega equal to 0. Now omega equal to plus or minus 1, because this will be existing for plus values of omega and exactly symmetrical value will exist for minus omega. So x of j omega at omega equal to plus minus 1. So omega is equal to 1 means omega square will be equal to 1. So 1 upon under root of 10. So this is 0.3162. Omega equal to plus or minus 2, just simplifies 2 square. So here it is 0.2774. Omega equal to plus or minus 3. Here you find that the corresponding values of the magnitude at different values of omega, as we are moving away from 0 and towards infinity, the corresponding magnitude goes on decreasing. Now there is a symmetry property. Whatever value we are getting for negative, positive side, we'll also have it on the negative side of omega. So the magnitude response is symmetrical. Now let us see how to calculate the phase response. The corresponding phase will be written as arc tangent of imaginary part divided by real part. Imaginary part is omega, real part is 3. So at omega equal to 0, it will be 0. Omega equal to 1, I calculate minus arc tan of 1 by 3. So I have minus 0.3218. So just go on substituting different values and you will get the answer. At omega equal to minus 1, At omega equal to 1, it is minus 0.3218. At omega equal to minus 1, it will be 0.3218 because I am calculating arctan. Now, in this case, you will find that the corresponding angle goes on increasing. Fourier transform of continuous time aperiodic signal is a continuous function of frequency. It is not a discrete function as in case of Fourier series. So, if we take periodic signal in time domain and if you take Fourier series, you will get a discrete spectrum. And when you take aperiodic signal and take Fourier transform, it will be a continuous function of frequency, and it is also aperiodic. It is also not periodic. When the signal is aperiodic, the transform will also be aperiodic. Now, what is the physical significance of symmetry in the magnitude response? We see that we get symmetry in the magnitude response. The evaluation of Fourier transform uses exponential representation, e raised to minus j omega, right? A sinusoid or the cosinusoid of angular frequency is represented as, sine is represented as 1 upon 2j into e raised to j omega t minus e raised to minus j omega t. And cos is represented as 1 upon 2 into e raised to j omega t plus e raised to minus j omega t. So, sine and cosine functions are represented in terms of exponential functions. Now, what is the byproduct of this exponential functions? The representation uses the ranges of both positive as well as negative angular frequencies. Right. So, the frequency as determined by the number of oscillations per second is definitely positive. But when we are using the for mathematical convenience, when we are using these exponential functions, we get the negative frequency as well. And the corresponding information which is present on positive side, same is the information that is present on the negative side. So it has no physical significance attached to it. It is just appearing as a byproduct because we are using exponential signal representations. This exponential function is what? It is a unit vector that we have seen. It rotates. So as omega changes, it rotates. The magnitude is equal to 1. So this is the magnitude and phase response that is plotted for the signal called as e raised to minus 3t ut. So in this case, you find that the magnitude response goes on decreasing, and at 0 it is 0.3333 as we have seen. And this is the phase plot of the Fourier transform of the exponential signal. And here you will find that it is antisymmetric. Phase is antisymmetric and magnitude response is symmetric. Now consider a peculiar signal which is a rectangular pulse. This is a rectangular pulse existing between minus t by 2 to plus t by 2, and I want to find out, this is called as the rectangular function. It is represented as equal to a between minus t by 2 to plus t by 2 and equal to 0 otherwise. So this is a periodic signal. It is not going to repeat itself. It is only existing between minus t by 2 to plus t by 2. So for this a periodic signal, we can write down the Fourier transform. Sorry. So let us see how Fourier transform calculations will go. X omega is integration minus t by 2 to plus t by 2 because obviously it is existing only between minus t by 2 to plus t by 2. What is the amplitude? Amplitude is a exponentiation of e raised to minus j omega t dt. So if I take the integration, I have 1 upon j omega, minus sign is there, a into e raised to minus j omega t, integration between minus t by 2 to plus t by 2. So if I just put the values of t by 2 and minus t by 2, if I take this e raised to j omega t by 2 term first and then minus this, then this minus sign will go, and I'll have it as 2j into a sine omega t by 2 divided by j omega, which is equal to this j will cancel now, and I will have 2a sine omega t by 2 omega divided by omega. Now this 2 I will take it as omega by 2. Omega is 2 pi f divided by 2. So I will get it as the sinc function. And I will multiply and divide by t so that I will get whatever is there in this bracket, same in the denominator. So I can write it as the sinc function. Now just consider this. Now this is a rect function with capital T given by 0.2. In that case, how the sinc function would look like? The sinc function would look like this. The corresponding amplitude value will be 0.2 as a maximum, going to maximum, and there will be some, you can say, the bandwidth of this main loop. And when I make the corresponding time t as equal to 0.1 rather than 0.2, that means I am shrinking the corresponding time width in the time domain signal. The corresponding main lobe width in the frequency domain signal goes on increasing. Here the main lobe width increases and the magnitude of the signal drops. Here it was 0.2, now it has become 0.1. Right, so the magnitude has dropped and the main lobe width increases. So what conclusion we can draw? The zero crossings occur in a spectrum at a multiples of 1 upon t. As the pulse width decreases from 0.2 to 0.1, the zero crossings are separated apart. That means main lobe width increases, becomes twice exactly in this case, and the spectrum is spreading with the decrease in the peak amplitude. The spectrum is spreading. This is what is the essential requirement in case of spread spectrum technique. So we are using the same technique in the spread spectrum whenever we want to spread the spectrum of BPSK, binary phase shifting signal, for the application in communication engineering. So what we want to do is we want to expand the bandwidth of the signal, bandwidth of the spectrum by reducing the spectrum width, and then we try to use the number of BPSK signals to travel via the same channel. This is what is the requirement in case of the optical fiber communication, right? In optical fiber communication, we reduce the amplitude and we combine all the number of signals to pass through the same channel, and at the receiver end, again we despread the spectrum and get the signal back. Let us consider one more example for finding out inverse Fourier transform. So now, instead of taking a rectangular pulse in time domain, I have the rectangular pulse in the frequency domain. So the corresponding pulse exists and having value equal to 1 between minus w to plus w. Now let us take inverse Fourier transform. Xt is equal to 1 upon 2 pi integration minus infinity to infinity x of j omega e raised to j omega t dt. Now in this case, if you compare the formula for Fourier transform and inverse Fourier transform, you will find that there is a factor of 1 upon 2 pi, but the corresponding nature of the formula remains the same. In case of Fourier transform, you have minus j omega t here, and in case of inverse Fourier transform, you have j omega t here. So if we take the inverse Fourier transform 1 upon 2 pi, it is existing between minus w to w e raised to j omega t d omega. So if we just calculate this, you get 1 upon pi t sine omega t, and this is basically, it is also a sinc function. So what you understand, if the signal in time domain is a rectangular pulse, the signal in the frequency domain is a sinc function, and if it is a rectangular pulse in the frequency domain, you get a sinc function in the time domain. So sinc function in time domain is the pulse in the frequency domain, and a pulse in the time domain is the sinc function in the frequency domain, vice versa. So what is the conclusion? Note that the time domain rectangular pulse has a Fourier transform as a sinc function, and the frequency domain rectangular pulse also has inverse Fourier transform as a sinc function. Hence, if the function is a rectangular function in one domain, it is a sinc function in the other domain. Means what? If the function is localized in time domain, it will be width spread out in the other domain, and when the width of the rectangular pulse increases in one domain, then the width of the main lobe in the other domain goes on decreasing, and vice versa. This is exactly stated in Heisenberg uncertainty principle. So if the width of the pulse in the time domain is large, then the main lobe width in the frequency domain will be small, and if the rectangular pulse width is smaller, then the corresponding width in the frequency domain will be large for the main lobe width, right? So the resolution in time domain multiplied by resolution in frequency domain is always greater than or equal to 1. So Heisenberg uncertainty principle says that the corresponding if you want to get the resolution in time domain, you will have to sacrifice for the resolution in the frequency domain and vice versa. And when I say vice versa, it is having a duality property. So this phenomenon is called as the duality property. Now let us consider a triangular wave which is existing between minus t to plus t, which is given by 1 plus t upon capital T and 1 minus t upon capital T for 0 to capital T. And let us try to find out x of j omega. So x of j omega minus infinity to infinity. So I just put the value of xt here. It is existing between minus 1 to plus 1. So I can write it as minus t to 0, 1 plus t by t e raised to j omega tt, and 0 to t, 0 to t, it is equal to 1 minus t by t e raised to minus j omega t. So I am just putting the value of this function for negative values and positive values. So if I separate it from minus t to 0 and 0 to t. Now what I do, when I want to find out the integration of 1 into e raised to minus j omega t, it is straightforward. But when I want to find out integration of the product t by t into e raised to minus j omega t, I'll have to use integration by parts, and I'm using it as integration by part t into e raised to minus j omega t upon minus j omega plus e raised to minus j omega t omega square integration minus t to 0. So it is first term into integration of the second plus the integration of the derivative of the first one into the corresponding integration of the second term. So this is what is called as integration by parts. So whenever there is a product of the two terms, we use integration by parts. So here also we will be using integration by parts for calculating integration of t by t into e raised to minus j omega t dt. So when you simplify, you get this term as 2 upon t omega square 1 minus cos omega t. Now let us consider a signum function and let us try to calculate the Fourier transform. This signum function existing equal to 1 for t greater than 0 and equal to minus 1 for t less than 0. This is what is called as signum function. We write this signum function as limit a tending to 0 of e raised to minus at ut minus e raised to at u of minus t. So when a tends to 0, this tends to 1, so it is ut minus u of minus t. So when I write this signum function as a limiting case of two-sided exponential functions, I know how to correspondingly find out the Fourier transform for the exponential functions. So I can directly use this. So I take two different terms between minus infinity to 0 and for 0 to infinity, because this is ut which is existing between 0 to infinity, and this is u of minus t existing between minus infinity to 0. So I just put limit a tends to 0, I just find out the integration for this, same as we have done for e raised to minus 3t, that was 3 plus j omega, in this case it is a minus j omega, and in this case it is a plus j omega, right? So now what you do is you just evaluate this particular thing, it becomes 2 upon j omega. So this is 2 upon j omega for negative values, it is also there for positive values. But what happens at t equal to 0? T equal to 0, it is going to infinity. T equal to 0, that means, sorry, this is omega axis. So when omega is equal to 0, it will tend to infinity because it is 2 upon omega. Okay. Now consider Fourier transform of the unit step function. Now this unit step function, I can write it as half of 1 plus signum t. So it is half of Fourier transform of 1 plus signum t. So I can write it as 1 upon 2 into 2 pi delta omega For 1, I will write Fourier transform as 2 pi delta omega plus 2 upon j omega. So it is equal to pi delta omega plus 1 upon j omega. Right. So in this case, what is the difference? In this case, the corresponding function is 1 upon omega plus pi j omega, represented like this on positive as well as negative sides of omega, and at omega equal to 0, delta is equal to 1, so it is equal to pi, and 1 upon 1 plus j omega, and this term will tend to infinity in that case, plus this will become pi. Omega equal to 0, this will exist. At only omega equal to 0, this will exist. X of 0 is pi into delta omega. Okay, thank you.